A manager at a power company monitored the employee time required to process high-efficiency lamp bulb rebates. A random sample of 40 applications gave a sample mean time of 3.8 minutes and a standard deviation of 1.2 minutes. Construct a 90% confidence interval for the mean time to process, mu. Okay, so notice that we're trying to construct a confidence interval for the population mean because we don't know what it is. And we only have one random sample of 40 applications. So we only have one sample mean, okay? And typically, the population mean is equal to the mean of all sample means, basically, okay? So if you have all kinds of samples, each sample containing 40 applications, and you take the mean of all the means of these samples, you will get the population mean. But we only have one random sample of 40 applications and only one sample mean as a result, which is 3.8 minutes. All right? But there's somehow a way to construct a 90% confidence interval using just one random sample mean, using this formula here. All right? And notice that I drew this symmetric graph, a normally distributed graph, because we can use normal distribution, precisely the z distribution, because we're talking about a random sample of 40 applications. So the number of items is at least 30 and above. When it's at least 30 and above, the data is approximately normally distributed, right? So distribution of the random sample means is normal, approximately normal. So we know that the sample mean here is provided to us as 3.8. Okay? And this part here means the standard deviation of the sample mean. Okay? And the standard deviation of the sample mean, by definition, should be the population standard deviation divided by the square root of the number of items. In this case, there will be 40 applications, so the n is 40. So the n is 40. Now, you might ask, but we don't know what the population standard deviation is. Well, since we're talking about at least 30 and above applications, we know that this is approximately equal to the sample standard deviation divided by the square root of n. Okay? So sample standard deviation is shown to be 1.2 minutes. So we're going to do 1.2 and divide it by the square root of 40. Okay, so that will be what you got. The result is the standard deviation of the set of sample means. Keep in mind that this is not the standard deviation of the sample. It's the standard deviation of a set of sample means, right? So just like the population mean, or the mean of the sample means, this is the standard deviation of all sample means. There will be infinitely many sample means, basically, right? We're not quantifying it, but we know that we can use this formula to find this standard deviation of the set of sample means. All right, so that's going to be the result. Now, why does this graph make sense? Notice that 90% confidence interval, and suggested by this formula here, is that the sample mean is right in the middle, right at the peak here. So the sample mean is here. And notice that the formula says plus minus because we're going to the right of this sample mean point, and we're going to the left of this sample mean point, right? So the minus will take us to the left, and the plus will take us to the right, because anything we get here will be positive. Okay? And we know that thus 90% will be divided into two equal parts, because we know since the normal distribution is symmetric, we will have an equal half on, we'll have a half on the right side of the mean and the left half on the left side, obviously, right? So for the same reason, 90% can be divided into two equal parts. And as you can see, there is a 5% that we're not interested in and 5% on the right side as well. So the left and right sides will include the 5% that we're not interested in. So the overall, the alpha level is going to be 0.10, and that suggests that the 10% will not be part of the 90%, because we know the whole thing you know that the probability is equal to 1, right? We know the whole thing is 100%. We're only interested in the 90% confidence interval. So the 10%, the 5 on the left and 5 on the right, are the parts of the total area that we're not interested in. Now, how do we find, and notice this means that the alpha divided by 2 is going to be 0.05. Right? Now, how do we find the z-value of the alpha over 2, or the z-value that pertains to 0.05 remaining probability? We basically have to understand that the probability table starts from the very beginning, and it starts the counting of the area, right? It starts the countdown of the probability from here, from the beginning. And the probability of 1 is basically at the very end. So that means this point that we're interested in finding, the z-value for the remainder of 5% probability, is going to be the 95% probability already covered from left to right, right? So if you start from the left, we wind up here. That means this will be 95%, right? Or 0.95 in the z distribution table, right? So let's find this value. So as you can see, this is already the positive z, right? These are the positive z's, as you can tell here. This row, this column is the positive z's, and this row is the positive z's. Okay? And what does that correspond to? Notice that I'm bringing up positive z's and negative z's because, again, we're talking about symmetry, and I'm talking about this half. This half of the graph, of the normal distribution symmetric graph, are all positive z's. Okay? Because the z-value typically here is 0. Okay, so right at the mean, the z-value is 0. It gets positive on the right and negative on the left. That's why you see minus z here. Okay, so we're talking about this half only for this normal distribution table. As you can see, it corresponds to what I just said. The z-value is 0, and that's exactly 50% probability. Notice that the probability values are inside the table, and they start from 50% or 0.5, because that's where the z-values start to be positive. And that means we've already covered the 50% probability, or the 50% of the total area, the entire left side, right? 45% plus the 5% that is outside of the confidence interval, right? So that's 50%. So that's why the probability table starts from 0.5. Now, remember that I just said that this point corresponds to 95% probability in the probability table, right? Because we have 5% plus 45, that's 50, plus another 45, it ends here, that's 95%. So let's find the z-value at the 95%. That means we have to have 0.95. So where is that? There's no 0.95, but we can use this point as a reference. That's about 95%, but we can be even more precise. Let's find this point. Let's find the z-value corresponding to this probability point. That is going to be 1.6, but that's not everything. There's also the top z-value of 0.05. So notice that 1.6 has to be added to this, right? Because this is the 100th place, the 5, and this is the 10th place, right? So basically, whatever probability value, target value you find, you have to be aware of the z-value on that row and also that column, right? So the column z's and the row z's meet together at a specific probability value. So in this case, we're interested in this value. So we know that 1.6 for the z and the column z value 0.05 meet there, and you have to sum these up, right? So the z value corresponding to the alpha over 2, which is 0.05 value, is 1.6 plus 0.05. But again, that's not precise, right? That's not precise because this corresponds to 0.9505. But we're interested in exactly 0.95, the exactly 95%. Notice that if you take these two, because these are equally away, these two values are equally away from 0.95. So if you sum them up and divide them by 2, you will get the average, which is exactly 0.95. So we might as well play around with the averages of these two z's, right? Because we know, you know that they're in the same row, so 1.6 will not be touched, but we have to play around with these columns, obviously, right? If we're trying to find the average. And the average, of course, will be between these, 0.4 and 0.05. And the average, of course, will be 0.045, right? That's easy to calculate. So as a result, it should be 1.645, right? That would be, as you can see, 0.045 is going to be the average between these two, right? And we added on top of 1.6. So once again, is going to be 1.6 plus the average of these two values. All right, and if you divide them, you will see what we're going to get. That's going to be 0.045. And as a result, this is equal to 1.645. And of course, you can use the calculator to find this value. That will be easy. But I'm just showing you how to use the table because in this case, we didn't need to use the calculator to find this value. All right, so going back, we already found the z value. It's 1.645. All right, so now let's use this formula. So we take the sample mean, 3.8 plus and minus the z value we found it, 1.645, times the standard deviation of the set of sample means, and that is 1.2 over square root of 40. All right, so that's going to be what? That's going to be first finding the leftmost limit. It's going to be 3.8 minus 1.645 times 1.2, well, times, let me indicate it like that, times 1.2 over square root of 40, and then 3.8 plus 1.645 times 1.2 divided by square root of 40. So the leftmost limit for the set of sample means, or the leftmost limit for the population mean, the true mean, mu. All right, so that's what it is. And as a result, this is equal to 3.49 being the leftmost limit and 4.11 being the rightmost limit for the population mean, or the true mean of the time required to process high efficiency lamp bulb rebates. So what does that mean? How do we interpret this result? It means we are 90% confident that the true, and we can say population mean time will be between 3.49 and 4.11 minutes. Okay, so that's all it means. Okay, the mean processing time will be between 3.49 and 4.11 minutes, and we're only 90% confident that it's going to be the case. Let's say if we were talking about a higher confidence interval, then obviously the points would be further apart. We would have a smaller point, a smaller number for this leftmost limit and a larger number for this rightmost limit. And notice one final thing I want to say before we stop is that you might say, why did you use the positive z? Because there's also a negative z, and that's absolutely true. Notice that due to symmetry, the z that we found can be simply negated as well. Okay, so if you were to negate it, if you were basically to use a negative, you would still be correct. Even though the 0.05 is the positive, you could use the negative in the formula, because the 5% is symmetric, that leftover area, with the 5% on the right. And notice that if you use the minus, you would still be correct, because the plus minus makes sure that you will have different halves, right? The two minuses would give you this result, and the plus and minus would give you the left result here. So it's fine. You could still use the negative if you wanted, the negative z. But it's always easy to just think of the positive side on the right side of the normal distribution table, just to make it easy so you don't have to think of negatives, etc. You know by definition that normal distribution is symmetric with respect to the mean, right? So both sides, the z's will be basically different by their negated versions of each other. Okay? So that's it, and I hope this was helpful. Thank you so much for watching, and see you in the next video.